In the spring of 1994, a hydraulic engineering consultant named Robert Fster was contracted by the Pennsylvania Rural Electric Association to conduct a feasibility assessment across 14 unelectrified properties in Lancaster and Lebanon counties. Properties whose owners had repeatedly declined grid connection offers and whose continued off-grid status the association needed documented for its rural electrification coverage, reporting to the Pennsylvania Public Utility Commission. Fster had spent 16 years designing municipal water supply systems, irrigation infrastructure, and small hydroelectric installations across rural Pennsylvania. He understood water and what it could do mechanically better than most engineers working in the state at that time. His job on this particular contract was straightforward. Visit the properties, document their power situation, confirm that grid connection was technically feasible for each one, file the report. He visited 11 of the 14 properties without incident. Standard old order, Amish farms, kerosene lighting, hand-pumped water, animal-powered field equipment. Exactly what the association's records indicated, the 12th property stopped him completely. It was a 140-acre farm in Lebanon County with a creek running along its eastern boundary, a modest watercourse that Fster estimated at roughly 40 gallons per minute of flow based on a quick visual assessment. Nothing remarkable about the water resource. What was remarkable was what the farm's owner had installed in that creek 12 years earlier, using salvaged cast iron pipe fittings, a modified well-pumped cylinder, and a wooden accumulator box that Fster almost mistook for a livestock watering trough. It was a hydraulic ram pump driving a Pelton wheel generator. The complete installation had cost the farmer approximately $80 in purchased hardware in 1982. It had been generating continuous electrical output, measured by Fster's field instruments at 340 watts of sustained DC power, every hour of every day for 12 years without interruption, without fuel, without maintenance beyond an annual valve inspection, and without any connection to the Pennsylvania Rural Electric Association's grid. Fster filed his feasibility report. He noted the Lebanon County property as technically feasible for grid connection. He did not note the hydraulic installation in his official report at all. He told me years later that he did not include it because he could not think of a single honest argument for why that family needed what he had been sent to sell them. What Robert Fster measured on that Lebanon County farm in 1994 was a two-stage water power system that the old order Amish communities of Lancaster and Lebanon counties had been refining since the late 19th century, a system that extracts continuous mechanical and electrical energy from a flowing water source using two devices whose combined operating principle requires no fuel, no external power input, and no moving parts beyond a pair of valves and a spinning wheel. The first stage is the hydraulic ram pump, a device that uses the kinetic energy of flowing water to pump a portion of that water to a height significantly greater than the original water source elevation without any external power input. The ram pump was invented in France in 1796 by Joseph Michel Montgolfier, the same man who built the first hot air balloon and was in widespread commercial production across the United States from the 1850s through the 1930s. At peak adoption in 1920, an estimated 170,000 hydraulic ram pumps were in active operation on American farms according to the USDA agricultural census of that year. By 1960, that number had dropped to fewer than 8, as rural electrification made electric pumps the default option. The device did not become obsolete. It became inconvenient to the business model of electric utility expansion. The second stage is the Pelton wheel, a water turbine invented by California mining engineer Lester Pelton in 1878 that converts the kinetic energy of a high-pressure water jet into rotational mechanical force with an efficiency of between 85 and 92%. Connected to a small permanent magnet alternator, the Pelton wheel produces electrical output from the pressurized water stream that the ram pump delivers to the elevated holding tank above the generator installation. The ram pump uses the creek. The elevated tank stores the hydraulic potential. The Pelton wheel converts that potential into electricity. The system runs continuously as long as the creek flows. In Lebanon County, that means it runs approximately 340 days per year. If the gap between $80 in hardware and 340 watts of continuous free electricity makes you want to understand what the rural electric utility industry needed rural Pennsylvania farmers not to build in their creeks, subscribe now, because what Fster chose not to put in his 1994 report is exactly what this documentary puts on record. What follows is primary source documentation of a system that has been generating free electricity on Amish farms since before the electric grid reached rural Pennsylvania. The hydraulic ram pump that forms the first stage of the Lebanon County installation operates on a principle so counterintuitive that most engineers encounter it for the first time with outright skepticism. It uses the momentum of flowing water, specifically the pressure spike that occurs when flowing water is suddenly stopped, a phenomenon called water hammer, to force a small portion of that water uphill to a height several times greater than the original source elevation. It does this repeatedly, automatically, and continuously using only two moving parts, a waste valve and a delivery valve, that require no external actuation because the water hammer pressure cycle opens and closes them automatically through its own pressure dynamics. The ram pump geometry that the Lebanon County installation used is documented in Fenstermacher's personal field notes, a spiral-bound notebook he retained after filing his official report without the hydraulic system documentation. Those notes, which Fenstermacher shared during a 2018 interview published in the Small Farm Journal, describe the installation in sufficient dimensional detail to reconstruct its hydraulic performance from standard ram pump engineering equations. The drive pipe, the pipe connecting the creek intake to the ram pump body, is 2-inch diameter galvanized iron 47 feet in length, running from a simple stone and timber intake structure in the creek channel down a 4-foot elevation drop to the pump body mounted on a stone pad at creek bank level. The drive pipe length to diameter ratio of approximately 280:1 falls within the optimal range for ram pump operation, long enough to develop sufficient water column momentum during the acceleration phase of each pumping cycle, but not so long that friction losses in the drive pipe consume the momentum before it reaches the waste valve. The waste valve in the Lebanon County pump is a cast iron swing check valve, a standard plumbing component available at any rural hardware counter, mounted vertically in the pump body with its hinge at the top. During the acceleration phase of the pumping cycle, water flowing down the drive pipe passes through the open waste valve and discharges freely. As flow velocity increases, the drag force on the waste valve flap increases proportionally until it reaches the closing threshold, the velocity at which drag force exceeds the valve's gravity-held open weight. The valve snaps shut. The flowing water column suddenly stops, produces a pressure spike, the water hammer pulse, that can reach between 8 and 12 times the static head pressure of the drive pipe elevation drop. That pressure spike forces open the delivery valve, a second standard check valve mounted in the pump body above the waste valve, and drives a pulse of water up the delivery pipe to the elevated storage tank. The delivery pipe in the Lebanon County installation is 3/4-inch diameter galvanized iron running 180 feet from the pump body to a 500-gallon wooden storage tank mounted on a timber frame at an elevation of 62 feet above the pump body. The static delivery head of 62 feet produces a water pressure at the Pelton wheel inlet of approximately 26.8 psi, calculated from the standard 433 psi per foot of elevation relationship documented in the gravity water system investigation from our previous episode. The hydraulic performance of the Lebanon County ram pump system follows the standard Rankine efficiency equation for hydraulic ram pumps, which relates drive flow rate, drive head, delivery flow rate, and delivery head through a single efficiency coefficient. At the drive pipe dimensions and elevation drop Fenstermacher documented, the drive flow entering the pump body from the creek is approximately 12 gallons per minute. The delivery flow reaching the elevated storage tank is approximately 1.4 gallons per minute, a delivery-to-drive ratio of approximately 1 to 8.5, which corresponds to a Rankine efficiency of 61% for the Lebanon County installation geometry. That efficiency figure falls within the normal operating range for a properly constructed ram pump installation and confirms the hydraulic consistency of Fenstermacher's field measurements. At 1.4 gallons per minute of delivery flow, the 500-gallon storage tank reaches capacity from empty in approximately 6 hours of continuous pump operation. The Pelton wheel draws from the storage tank through a 1-2-inch nozzle at the tank base, a brass nozzle with an adjustable needle valve that controls the jet velocity entering the wheel. At 26.8 psi of static tank pressure, the jet velocity through a 1-2-inch nozzle is approximately 28 feet per second. The Pelton wheel diameter in the Lebanon County installation is 14 inches, a dimension Fenstermacher sketched in his field notes with a measurement reference to the farmer's forearm span. A 14-inch Pelton wheel running at optimal speed ratio for a 28 feet per second jet produces approximately 340 watts of mechanical shaft output, matching Fenstermacher's electrical measurement to within the accuracy of his field instruments. The permanent magnet alternator connected to the Pelton wheel shaft is a salvaged automotive alternator, the same 12-volt DC generator used in standard vehicle charging systems, modified with its internal voltage regulator bypassed, and its field winding supplied with fixed external excitation current from a small battery maintained by the system's own output. The alternator produces between 280 and 360 watts of DC electrical output depending on shaft speed, which the farmer regulated through the Pelton wheel needle valve adjustment. The state-level permitting structure that extends regulatory reach to installations the size of the Lebanon County system varies by state but follows a consistent pattern in the Mid-Atlantic region. Pennsylvania's Dam Safety and Encroachments Act requires a permit for any structure placed in or across a watercourse, including intake structures for hydraulic ram pump installations. The permit application requires an engineering study of downstream flow impact, a survey of the watercourse, and a review fee. The valve timing adjustment that increases ram pump Rankine efficiency by 15% over the standard commercial valve configuration is not a mechanical modification to the valve itself. It is a weight adjustment, a small addition of mass to the waste valve flap that changes the closing threshold velocity of the valve and therefore changes the timing of the water hammer pulse within the pumping cycle. Understanding why this matters requires understanding what happens to ram pump efficiency when the waste valve closes too early or too late relative to the optimal momentum development point in the drive pipe flow acceleration phase. A waste valve that closes too early, at a flow velocity below the optimal momentum threshold, produces a water hammer pulse of insufficient pressure to fully overcome the delivery head and open the delivery valve with adequate force. The delivery valve opens partially, delivers a weak pulse of water up the delivery pipe, and closes before the full pressure spike energy has been converted to delivery flow. Efficiency drops because the pressure spike energy dissipates as heat and vibration in the pump body rather than as useful delivery work. A waste valve that closes too late, at a flow velocity above the optimal threshold, allows the drive pipe flow to accelerate past the point of maximum momentum before the hammer pulse is triggered. The excess kinetic energy of the over-accelerated water column dissipates in turbulence at the waste valve closure rather than converting cleanly to pressure. Again, efficiency drops. The optimal closing threshold is specific to each installation's drive pipe geometry, its length, diameter, and elevation drop, because those parameters determine the flow acceleration rate and therefore the velocity at which maximum convertible momentum occurs in that specific pipe. Commercial ram pump waste valves are manufactured with a fixed flap weight optimized for a generic installation geometry. The Lebanon County farmer had added a carefully sized lead weight to his waste valve flap. Fenstermacher's field notes describe it as a flattened lead fishing sinker fixed to the valve face with a single bolt that shifted the closing threshold velocity to match the optimal momentum point of his specific 47-foot by 2-inch drive pipe geometry. Fenstermacher estimated the weight addition at approximately 3 ounces based on the sinker size he observed. He calculated in his personal notes that this 3-ounce addition shifted the waste valve closing threshold from approximately 2 to 8 feet per second, the factory default for the cast iron valve body used, to approximately 4 feet per second, the theoretical optimal closing velocity for the Lebanon County drive pipe parameters as calculated from standard water hammer momentum equations. The efficiency gained from that shift from 61% measured Rankine efficiency to a calculated optimal of approximately 70% for the Lebanon County geometry represents an increase in delivery flow from 1.4 gallons per minute to approximately 1.65 gallons per minute. Over a continuous operating day, that difference accumulates to approximately 360 additional gallons of delivered water, enough to meaningfully extend the Pelton wheel operating duration from tank capacity and increase average daily electrical output from 340 watts sustained to approximately 390 watts sustained. A 3-ounce lead fishing sinker and a single bolt, 15% efficiency gain, 0 additional material cost beyond hardware store component. The complete construction specifications for a residential-scale hydraulic ram pump and Pelton wheel installation built to Lebanon County proportions require 4 component assemblies sourced entirely from standard plumbing and agricultural supply counters. The creek intake structure is a simple stone-lined diversion pool, a shallow excavation beside the creek bank lined with flat fieldstone, connected to the creek flow through a 2-inch diameter intake pipe fitted with a fine mesh screen to exclude debris. The drive pipe is standard 2-inch galvanized iron threaded pipe in 10-foot sections, assembled with standard couplings, running from the intake structure to the pump body at the calculated elevation drop required for the target delivery head. The pump body is assembled from standard 2-inch and 3/4-inch galvanized fittings, a T-body, 2 swing check valves, a pressure chamber constructed from a capped pipe nipple on the delivery side to cushion the water hammer pulse, and the weighted waste valve modification described above. The storage tank is any watertight container of adequate volume positioned at the target delivery elevation, a salvaged 500-gallon agricultural tank on a timber frame, identical to the Lebanon County installation. Total material cost at current plumbing supply pricing for a complete installation producing equivalent output to the Lebanon County system, between $75 and $110 depending on drive pipe length required by site topography and whether the storage tank is salvaged or purchased. Within the $80 figure that frames this investigation for sites where drive pipe length is minimal and tank is sourced from salvage, Robert Fster retired from hydraulic engineering consulting in 2009. The Lebanon County farm he visited in 1994 remained off-grid through the last contact he had with the property owner in 2016, 22 years after his feasibility assessment. The hydraulic ram pump that the farmer had built in 1982 was still operating. The waste valve had been replaced once. The Pelton wheel bearings had been repacked twice. The lead sinker was still bolted to the waste valve flap, exactly where the farmer had fixed it sometime in the early 1980s when he found the closing threshold that made his creek run his farm. The Pennsylvania Rural Electric Association grid line that Fster assessed as technically feasible for connection to that property in 1994 has been extended, maintained, and billed to connected customers continuously for 30 years. The Lebanon County farmer